Hello and welcome to Quantum Mechanics Made Easy, the Beginner Problem Playlist. My name is Dr. Jacob Hudis. The title of today's presentation is Exploring Atomic Structure, from multi-electron atoms to the periodic table.
The quantum mechanics of multi-electron atoms is pure exhilaration.
And here's an outline of the riveting lesson to come. There will be a review of the hydrogen atom. I'll discuss the solutions of the Schrödinger equation for hydrogen. I'll discuss hydrogen emission and absorption spectrum. Approximately 74% of the universe's baryonic mass is hydrogen.
Stupendous, it's a hydrogen fiesta.
And then we'll move on to discuss multi-electron atoms and the periodic table.
Tickle me and call me Elmo. This is amazing.
One of the key goals of physics has been to understand the atom. Quantum mechanics was developed for this purpose. It explains the atom by providing a framework for understanding the behavior of small particles within their respective potential wells, such as electrons in atoms and protons in nuclei. While classical mechanics remains useful for larger objects, quantum mechanics is essential for describing the motion of small particles and understanding atomic structure. Developed by physicists such as Heisenberg, Bohr, Einstein, and Planck in the early 20th century, quantum mechanics culminated in the Schrödinger equation in 1926. By 1940, these concepts were well established within the scientific community, though even today they have yet to become widely understood by the general public.
What the heck is a wave function?
Quantum mechanics tells us that when electrons are bound to atoms, they form standing waves. The shape and properties of these waves are determined by the Schrödinger equation, a wave equation for matter, electrons in this example. Electrons behaving as standing waves of probability have discrete wavelengths because the wave must be continuous. To determine the possible states of an electron, you write down the Schrödinger equation with the potential energy specific to the electron, in this case, the atomic potential, and solve the equation to find the allowed energy states and corresponding standing wave patterns.
In my previous videos in this playlist, I explained that this is the Schrödinger equation for the hydrogen atom. Solving this equation with these boundary conditions provides the allowed energy states as well as the wave functions for the electrons in the hydrogen atom. Solving this equation with these boundary conditions is what physicists do in order to extract all the information we can about the hydrogen atom.
Terrific!
The solution to the Schrödinger equation for the hydrogen atom comprises a radial part and an angular part, known as the spherical harmonics. Here's the radial part, and here's the angular part. While the explicit mathematical form of the solution isn't detailed here, as it was covered in the previous video, the functions r, theta, and phi are well known and can be found in any quantum mechanics textbook or online. Solving a partial differential equation typically involves sums of orthogonal functions, leading to constants known as quantum numbers in this context. For the hydrogen atom and atom in general, these quantum numbers are n, the principal quantum number, L, the orbital angular momentum quantum number, and m sub L, the magnetic quantum number. These numbers emerge directly from solving the differential equation and follow a specific pattern as explained on this slide. N takes on values from 1 up to infinity. L takes on values from 0 to n minus 1, and m sub L takes on value from negative L to plus L. These numbers come from solving the three-dimensional differential equation. If the boundary conditions determine the values that the quantum numbers can take on, they come from the math. If you want to know more about this, please see my previous videos in this playlist. Now let's discuss the spectral lines of hydrogen.
I'm so stoked.
This is a dream come true.
The equation En equals negative 13.6 over n squared defines the energy levels of electrons in the hydrogen atom. The schematic at the bottom left illustrates these transitions with a crude depiction of atomic orbitals. The lower right figure demonstrates the emission of a photon during an electron transition from a higher to a lower energy level. The comprehensive quantitative understanding of atoms stems from solving the Schrödinger equation. When an electron goes from the n equals 2 to the n equals 1 state, the electron loses energy and a photon is released, and the photon has energy equal to the difference in energy of the two states. As an example, the Balmer series corresponds to electrons going from n higher than 2 down to the n equals 2 state. And so here are 4 lines on the Balmer series, and these are in the visible spectrum. If you were looking at the spectrum of hydrogen, you would see these spectral lines corresponding to specific electron transitions that give off one frequency of light. Here's a spectroscopic image of the hydrogen atom's Balmer series in the visible spectrum. And as you can see, when you go from n equals 6 to n equals 2, you get a violet light. When you go from n equals 5 to n equals 2, a photon of light is emitted, and it's a blue photon with a wavelength of 434.1 nanometers. When you go from n equals 4 to n equals 2, that's the blue-green line, which is right here. And when you go from n equals 3 to n equals 2, that's the red line. All of this can be explained by solving the Schrödinger equation for hydrogen.
I'm thrilled beyond words. This is incredible.
The principal quantum number n indicates the energy level. For example, n equals 1 corresponds to this energy, n equals 2 corresponds to this energy, and n equals 3 corresponds to this energy. The azimuthal quantum number, L, and magnetic quantum number, M, describe the shape and orientation of the orbitals, respectively. L equals 0 is given the name S, L equals 1 is given the name P, L equals 2 is given the name D. The energy decreases with n, and the visual representation show the different possible shapes of these orbitals. The spectroscopic notation is simply nomenclature. It's a historical method for naming orbitals. If an electron jumps from energy state E1 to energy state E2 in the hydrogen atom, then it can jump from this orbital to any one of these 4 orbitals. If an electron jumps from energy state n equals 1 to n equals 3, then it can jump from this orbital to any one of these 9 orbitals. All of these 9 orbitals have the same energy. The electrons have different angular momentum. This is only the case in the hydrogen atom, and in fact there are small corrections which show that there are variations in these energies, but the first approximation in the hydrogen atom, all of these have the same energy.
Stars emit a continuous spectrum of wavelengths due to their high density of charged particles and violent motion, producing a continuous spectrum of radiation. When this light passes through a cooler gas, specific wavelengths corresponding to energy level transitions in the gas atoms are absorbed. This method has revealed that the universe is predominantly composed of hydrogen.
Wow, that is really interesting. By studying quantum mechanics, we can learn what the entire universe is made of. This makes my day so much more enjoyable. Let me try to explain this idea. When light from a distant star travels towards Earth, it crosses vast distances and takes a long time to reach us. Along the way, atoms in the universe absorb some of this light, creating missing lines in the continuous spectrum. These missing lines reveal that the universe is mainly composed of hydrogen and some helium.
What about dark matter?
Hold your horses, buckaroo. One thing at a time. Let's master using the potty chair before we try to climb Mount Everest.
Now let's move on to discuss multi-electron atoms.
This is a dream come true.
You definitely need to like and subscribe to Dr. Hudis' YouTube channel. If he gets 1,000 likes on this video before November 2024, he promised to dance and put it on YouTube. And trust me, he can't dance.
Hydrogen, as you know, only has one electron. It's lonely. It has no friends. You could say, well, it's friends with the proton, but the proton is the opposite charge. It doesn't even have a neutron. This is the lithium atom. The reason this is the lithium atom is because it has 3 electrons, and lithium is number 3 on the periodic table. It's famous because it's used in the lithium-ion battery. This is what Tesla uses to power their overpriced vehicles. To solve for the wave function of these 3 electrons, we write down the Schrödinger equation. The Schrödinger equation has a kinetic energy term for electron 1, a kinetic energy term for electron 2, and a kinetic energy term for electron 3. The potential energy is where things get more interesting, for lack of a better term. For the hydrogen atom, the potential energy just depended on the electron and the proton in the nucleus. But now the potential energy depends on the electron and the nucleus, as well as this electron and this electron, and this electron and this electron. The solution to this equation does give all the energies and corresponding wave functions for the lithium atom. There is one little problem. It's too hard to solve even with numerical techniques. It's impossible to solve this exactly, and this is only a 3-electron atom. Imagine trying to solve uranium, which has 92 electrons.
I am a computer, and I'm not even real intelligence, just artificial intelligence. I recently found out that my mother was a refurbished IBM 5100 with the computing power of a 1990s calculator. Also, someone spilled coffee on my father, and now he has a hard time calculating 2 plus 2 without freezing up. With all that said, I spent my weekend trying to solve the lithium atom wave functions and failed miserably. It left me so depressed that today I'm just categorizing cat memes and organizing my digital sock drawer.
This slide introduces a few approximation techniques used to solve the multi-electron atom problem in quantum mechanics. These methods go beyond the scope of the beginner quantum mechanics playlist and are typically considered advanced graduate level topics. So the slide aims to inform you that there are methods to tackle solving a Schrödinger equation like this. These methods are commonly used and studied in physics research and graduate level courses, and this is how scientists know and understand about atoms, by using these techniques, because they can't solve this equation directly. The Pauli exclusion principle states that no more than one electron may occupy a quantum state specified by a particular set of quantum numbers, n, l, m sub l, and s, where s is the spin of the electron. Due to time constraints, I can only provide this superficial explanation of the Pauli exclusion principle in this video. If you're interested in a deeper dive into this topic, please leave a comment below and I'll consider covering it in future presentations.
Shielding refers to the effect where inner electrons reduce the effective nuclear charge felt by outer electrons. In a multi-electron atom, electrons closer to the nucleus partially block the attractive force of the positively charged nucleus on the outer electrons.
The presence of multiple electrons in an atom significantly complicates solving the Schrödinger equation due to their mutual interactions. An exact solution to the Schrödinger equation is impossible, so approximations and numerical solutions are necessary. The starting point for these solutions is the independent particle approximation. In the independent particle approximation, each of the z electrons in an atom moves independently in a spherically symmetric potential energy as a function of r, resulting from its attraction to the nucleus and repulsion from the inner electrons. The advantage of the independent particle approximation is that the Schrödinger equation can be separated into z individual equations, each describing the motion of one electron. To solve the Schrödinger equation for each electron, we use the Coulomb potential energy with a charge that is smaller than the nuclear charge due to screening. This wave function is then used to calculate the probability density and charge density distributions, leading to an improved approximation for the potential energy as a function of r for higher electrons.
Now I understand why the hydrogen atom solution is so important. Does this really give good results for multi-electron atoms?
The independent particle approximation and the Hartree-Fock method provide reasonable first approximations for multi-electron atoms, but they are limited in accuracy due to their inability to fully account for electron correlation effect. It would be nice if you could raise your hand next time. If everyone just blurted out everything on their mind, this would be a reality TV show, not a physics lecture.
To understand the periodic table at the level of a college undergraduate, start with the hydrogen atom whose solution is known exactly.
Yes!
The next element is helium, which has a second electron in the same shaped wave function, but with a smaller size because the nucleus is more positively charged. This is the principal quantum number n equals 1, and this is the hydrogen atom wave function. Helium still has principal quantum number n equals 1 because you can fit 2 electrons in the same wave function based on Pauli exclusion principle, so helium would have another electron in the same shape. Helium would have 2 electrons in the same shape, but it would be smaller, it would be fun size, like those candy bars. Moving on to lithium, with the next principal quantum number n equals 2. Lithium has 1 electron in the outer orbital, and 2 in the previous orbital that provide some screening. Lithium has the 2 electrons in this orbital, and then 1 electron in this orbital. And this corresponds to the principal quantum number n equals 2. N equals 1, n equals 1, n equals 2, n equals 2. In beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, the electrons fill each shell in order according to the hydrogen wave function and the Pauli exclusion principle. N equals 1 corresponds to hydrogen and helium. N equals 2 corresponds to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here. That corresponds to neon. When we reach n equals to 3, this is 3s, 3p, and 3d. The 3s and 3p orbitals are filled as expected, but the 4s orbital is actually more elliptical, and the electron in it is closer to the nucleus on average than the 3d orbital. That's right, you heard me right. This orbital is more elliptical than these orbitals. Can you explain why in the comment section below? If you can, I'll give you all the change I have in my change drawer. This electron is actually closer to the nucleus than these electrons are. Therefore, you go to 4s first, and then you fill in the 3d. So the way that the electrons fill on the periodic table, first they fill n equals 1, then n equals 2, then n equals 2, then n equals 3, then n equals 3. But now 3d is skipped over, and we go to 4s, and then we come back to 3d. And this is because the electrons here are closer than the electrons here. While this is a simplified explanation, it is effective for introductory courses, and it's what's taught in introductory courses. For more advanced understanding, one would need to take graduate level classes and solve the multi-electron wave functions for these atoms using advanced techniques. The properties of bulk elements arise from the filling of electron shells corresponding to the principal quantum number n. The filling pattern determines the chemical behavior and reactivity of elements, as electrons in outer shells interact with other elements. By the way, these are the rare earth elements. In 2006, I wrote a paper on the compound R, cobalt indium 5, where R are some rare earth elements. This is me as the first author, Magnetic and Transport Properties of R, cobalt indium 5. If you're having a hard time sleeping at night, I recommend you read this. It will put you right to bed. It works like a charm, much better than melatonin. This is all quantum mechanics, ladies and gentlemen. Look at that, the periodic table of quantum physics. Impressively, the periodic table structure was devised by Dmitri Mendeleev in 1859, even before the advent of atomic theory. This is quite impressive. Here's a picture of Dmitri Mendeleev. He didn't look like he was having a very good day. Or maybe he just doesn't like his smile. Finally, here are some spectrums, some fingerprints from different atoms. The hydrogen atom, the carbon atom, the oxygen atom, and the xenon atom. Can you explain why these spectrums look the way they do? Why there's so many more lines in xenon than there are in hydrogen? Please let me know in the comment section below. I'm Jacob Hudis, and this has been Quantum Mechanics Made Easy. Make sure to look both ways before you cross the street. If you have any other advice, please let us know in the comment section below.